Good evening, everyone. Today in our class, we will be discussing uh, flow through uh, around the body of a immersed body in a fluid. So, before starting today's session, I would like to wait for a few minutes more people to join for this. Okay, so welcome to today's session. Today we'll be discussing flow past blob bodies. And what are these terms mean, we will discuss one by one in today's lecture. So let me introduce myself. I am Smita Mondol. I am a PMRF research scholar doing my PhD in Chemical Engineering Department of IIT Madras, and I am taking this NPTEL lecture as a part of my teaching assistantship for PMRF fellowship. So let's start today's session. So when we talk about a immersed body in a fluid, there are few forces that acts on the immersed body. Now this immersed body can be of different types. One body can be uh, perpendicular to the flow line of the fluid, and it can be completely aligned with the streamline of the fluid. So we will discuss one by one that how the shape of the body and other factors affect the um, drag forces, or what are the drag forces exist to have significant effect for creating different kind of uh, flow regimes. So let's start with simple introduction of drag force. So when the fluid flows past any object, it's tend to drag the object along in the direction of the fluid flow. In this video, you can see that these are the streamlines and this is the object in between the streamline. So any kind of flow that is flowing over the object is tends to drag the object along the direction of the flow. So this is the flow direction. So what is happening that by Newton's third law of motion, an equal and opposite net force will be exerted by the body on the fluid. As the fluid is dragging the object, this is one object. Now the fluid is flowing over the object, so that fluid will also drag the objects by the drag force. So by the Newton's third law of motion, an equal and opposite net force will be exerted by the body on the liquid. If an object is moving through a stationary fluid, the drag tends to slow down the object movement. But if the object is stationary and fluid is flowing over the object, then the drag tends to move the object in the direction of the flow. So this drag force that we are talking about, this drag force comprises two components. One is pressure drag, or also it is known as form drag, which is based on the pressure difference between the upstream and downstream surfaces of the object. And second one is skin friction, which results from the viscous shear of the fluid flowing over the object surfaces. So basically, drag force, two types of drag you can expect. One is form drag and another one is skin drag or viscous drag, you can say. So the form drag is the result of result forces normal to the surface of the object, and the skin friction is the resultant of the result forces which will be tangential to the surface. So the surface is like that. So perpendicular to the surface, that will be pressure difference. Due to pressure difference, that will be your form drag, and the tangential one, which is tangential skin friction, that you can say, that is known as that is due to tangential part to the surface. So we were talking about this this form drag and skin friction. The total drag of any object will be the summation of the pressure drag and skin friction drag. So when the drag is primarily due to viscous force or viscous drag, the body is streamlined. See, there will be, the body is streamlined. But when the drag force is primarily due to pressure drag, there is high pressure and low pressure zone. So there will be that body will be called as Bluff body. A perfect fluid flowing past an infinity long cylinder is represented as streamlines which are arranged such that the flow through each streamline is fixed. The streamlines flow over cylinder and all the forces are balanced back and front, top or bottom, and there is no form drag. So this is what a perfect fluid means. But in reality, also the perfect fluid cannot transfer shear stress. So there we cannot expect any kind of viscous drag. But in reality, the real fluids, there is pressure buildup on the front of the surface as the fluid is slowed and the streamlines are redirected round the cylinder. So there wakes are formed, and this kind of phenomena is observed for the real fluid. As the fluid flows over the cylinder, the fluid separates into wakes, which is a low pressure region. There is therefore significant presence of the foam drag, which is due to the pressure difference. There is also skin friction drag as the fluid passes over the surface. So when we talk about drag force, so you can see a flat plate if you are taking, and the flow of direction of the flow which is parallel to that flat plate. Initially there is a uniform velocity, and then the velocity profile becomes like this. So when the wall of the body is parallel to the direction of the fluid flow, as in case of the thin plate, flat plate, the only thing that we can expect here, that is only the wall drag force is present, that is shear force. But when the body on the object body is perpendicular to the flow of liquid or fluid, then there is difference in the pressure in the front and in the back of the object. And due to the pressure difference, suppose this is P1 zone and this is P2 zone. So here basically P1 is greater than P2, and due to this pressure difference, the foam drag or she the foam drag is only present. So this is what we want to mean, that how the drag force and the pressure due to pressure difference, the foam force are creating. It depends on the geometry of the object that is immersed in the fluid. So when we talk about any kind of object which is not exactly parallel to the fluid flow, also not exactly perpendicular to the fluid flow, then suppose they are making an angle with the fluid flow direction. So this is one an object with area of dA. You can see this is one object dA, and it is making an angle with the flow direction, that is the direction of flow. So this is also direction of flow. So it is, this angle is making a degree of 90 minus alpha. And if you resolve the force component on this angle, you can see that that is the shear force. It is tau sine of alpha dA, and it will be, that is coming on the direction of the fluid flow, and due to the pressure which is acting always perpendicular to the surface, so it is making a component of the pressure which is P cos alpha into dA, which is the component of the form drag, and tau sine alpha into dA, this is the wall drag. So what is the net force that is acting in the direction of the fluid flow due to the presence of the immersed body at an angle of 90 minus alpha? That will be summation of these two, wall drag and form drag. So any kind of inviscid, incompressible and irrotational flow, which is also known as potential flow, the net drag force on a body is zero. This is one assumption of the potential flow, that viscosity is zero, there is no compressibility and irrotational, it is irrotational. So that kind of flow is known as potential flow, and in potential flow there is no wall drag since viscosity is zero for that case. So here from this part we are considering a case of potential flow where the wall drag is zero because viscosity we are assuming to be zero, and no form drag because pressure distribution is also symmetric around the body. Hence for a potential flow the net drag is also zero. But if we talk about real case scenario, in real fluids, the boundary layers, separation of boundary layers, and wave formations always happen. They create the drag and they participate in the form drag and wall drag as well. Now, when we discussed about the drag force, the next thing comes under consideration, that is the drag coefficient. So, suppose we are taking a immersed sphere which is placed on along the streamline of the flow. And now if we consider the projected area for the sphere, it is AP. And you can see the fluid streamlines follows a path around the sphere. The initial fluid velocity is u naught or v, and we are assuming that the velocity v is constant over the projected area. So for this kind of scenario, if we want to define the drag coefficient, first of all, we hope that we know that friction factor is defined as shear stress divided by uh, density into velocity height. Similarly, drag coefficient is also a dimensionless quantity which is used to quantify the drag or resistance of an object in the fluid environment. Drag coefficient is denoted by CD, which is equals to FD by AP. FD is the drag force divided by AP is the projected area, and rho V square by 2, that is similar to the friction factor. So from the dimensional analysis, this drag force CD of a smooth solid in an incompressible fluid depends upon obviously Reynolds number and also necessary shape factor of that geometry. So if you calculate this equation, you will get FD equals to half of CD into rho into AP. This is the formula for FD. So for a given shape, this CD drag coefficient is always function of Reynolds number of the particle. And how the particle Reynolds number is defined in a fluid? It is defined as diameter of the particle into density and velocity of the fluid by velocity and by viscosity of the fluid. So the definition of the drag force and the definition of the drag coefficient is important when we are going to discuss rest of the derivation. So now we are going to define the drag coefficient for different flow regime, and we will consider a spherical particle for this. Before going to Stokes regimes or laminar flow regimes, we need to know and have a glance on a Stokes law. What is a Stokes law? According to the law, the drag force Fd experienced by a spherical particle flowing through a viscous fluid is given by 3 pi mu v and dp, where mu is the viscosity, v is the velocity, and dp is the characteristic length. And we are considering the sphere, so the characteristic length is the particle diameter. So in this case, we are having some assumptions of the Stokes law, that is, particle must be solid, smooth and spherical. Particle must be uniform density, sufficiently large as compared to the molecules of the fluid, so that the thermal motion of the fluid molecules doesn't interfere or affect the solid particles, and particles should not interfere with each other during the free fall. The suspension should not have any turbulence, so the flows of the whole system be at laminar. So now your uh, next target will be derivation of the drag coefficient for a spherical particle in a Newtonian fluid when there is in Newtonian fluid when their particles Reynolds number is less than 0.1. For that case, you have the formula of Fd equals to So here we have Ft equals to this for a Stokes law regime. So for this, CD will be Fd by Ap divided by rho v square by 2. So you just put all of the thing pi by 4 dp square for the spherical particle. You are having zero point 0.5 into rho into v square. From that you will get 24 mu by rho v dp, which is also denotes that CD equals to 24 by Reynolds number of the particle. So we have just calculated that how the drag coefficient will be for case of when it follows the Stokes law. Now related to this, we also have to learn this Stokes law regime, that um, this Stokes flow is also known as creeping flow. So we are following the same particle. For a spherical particle, we are going to define creeping flow, that how we have defined for the Stokes flow. So this creeping flow describes the fluid flow in which the inertia is insignificant. The viscous and the pressure forces exerted on the fluid are large or greater than the inertia. So fluid with high viscosity have difficulty in flowing, and they usually travel in a creeping motion. Even though the inertia is negligible in these fluids, they are dominated by the internal friction. Fluids that creep in the flow are non-turbulent and never make spinning vortices in the flow. Creeping flow fluid creep around the obstacles rather than becomes turbulent. So this creeping flow is also known as Stokes flow. In the creeping motion of the fluid, viscous force dominant over advective inertial force. In fluids, the creeping flow is a laminar type of flow where the streamlines are parallel to each other. The velocity of creeping flow is very low. Reynolds number, which is a dimensional number that gives the relation between the advective inertial force and the viscous force. Here the Reynolds number is directly proportional to the density of the fluid and the velocity of the fluid, and it is inversely proportional to the dynamic viscosity of the fluid. So for creeping flow, which is occurring at a very low velocity, here the Reynolds number is very less than 1. So when Reynolds number is less than unity, inertial effect can be ignored and taking into account only the viscous resistance. The fluid flow is non-chaotic for creeping motion, and fluid flow that travels in a creeping motion is time irreversible. Next, we are going to understand the Reynolds number for different flow regimes over the sphere. Suppose we are having different Reynolds number categories, and from there you can see that it is of creating vortexes, and then it turns to be fully turbulent wake flow. So at very low Reynolds number, which is less than 10, the streamline remained attached to the sphere and no separation occurs. This flow is completely laminar. This is called creeping flow. When it is 10 to 40, the Reynolds number, the streamline mainly is still attached, but there are some little vortices that starts to form at the back of the sphere. When at 40 to 2 into 10 to the power 5, that is turbulent regime, it belongs to this category, that is the transitional laminar to turbulent, or you can say transition regime, and there the large vortices or wakes starts to form. This regime, the coefficient of drag becomes very high, and when it is completely or fully turbulent regime, the boundary layer is formed, and this turbulent boundary layer will cause a smaller wake region to form, and the coefficient of drag will be compared, it is um, small compared to the transitional regime. So, in the fully turbulent regime, what is happening that the initial force in the flow dominate over the viscous forces. The boundary layer becomes turbulent and relatively insensitive to further increase in the Reynolds number. The wake structure and the separation of the point stabilize, which indicates that the pressure distribution around the body no longer changes much with the increasing velocity. Now we are going to learn about dependence of the drag coefficient on the Reynolds number. So there will be one graph. There will be one graph that will tell you this is the drag coefficient and this one is the Reynolds number. This is 10 to the power minus 1, 10 to the power 3, 10 to the power 5. This one is Reynolds number. So in the regime of 10 to the power minus 1 or zero point 0.1, this zone is known as Stokes' law regime. This one is the transition. This one is the transition regime and this one is the turbulent regime and this one is the highly turbulent. So here it is also known as turbulent or Newtonian. So we have already derived that for Stokes regime, CD equals to 24 by RE. For Newtonian's law regime, it is CD equals to 0.44, which is independent of the Reynolds number. So this graph is very important to understand the relation between the drag coefficient and the Reynolds number. Similarly, when this is a well known graph for the drag coefficient and Reynolds number, it is we are not talking about spheres only. This graph can be for different kind of shapes and the structure of the particle, that is for cylindrical type or disc type. This is the Stokes law which follows a straight line part, and for the sphere and cylinders you have the different graphs. So this graph will be helpful that if you calculate the Reynolds number from there you can simply go up and you can have your drag number, and vice versa, that if you had the drag coefficient number you can go like this and you can have like cylinder, you go down, you will have the Reynolds number. So this kind of graph is useful to basically know the drag coefficient value for a calculated Reynolds number for the fluid flow condition. Now the part we are going to discuss, that is the forces. Those are acting on any kind of particle which is submerged in the fluid. Any particle captured within a field is subjected to force acting on it. Now the field strength describes a measure of the force that a field exerts on a mass or on a particle. So these three kind of force we can experience. One is the external force, that is the gravitational force or centrifugal force, and another one is the drag force, another one is the buoyancy force or buoyant force. We are basically going to discuss about the gravitational force and centrifugal force. So this gravitational force is defined as force per mass of unit mass acting on a body. The gravitational force is expressed in terms of volume of the particle, that is F equals to, you you just break down this mass equals to volume into density into g. So for small particles with a low terminal velocity, motion under the effect of the uh, gravitational force is very slow. So when you want to speed up the process in the presence of the centrifugal force with the angular velocity omega, you just have to calculate the centrifugal force equals to mr omega square, where r is the distance between the particle and the axis of rotation. And under a centrifugal force, the particles move readily outwards. So when we are talking about buoyant force, which acts parallelly with the external forces but in the opposite direction, you can see this picture. In general, the direction of the movement of the particle, which is always relative to the fluid, may not be parallel with the direction of the external force or buoyant force, and then the drag force makes an angle with other two forces. This kind of real life examples we can also able to see. So this kind of thing is known as two-dimensional motion, which needs to be resolved into components. But in this class, we are going to focus on the one-dimensional forces only, which is acting on the particle. Next, we are going to discuss on the differential settling topic. So the main thing that we are going to discuss here, that differential settling, it acts on the, this is our beaker of different particles. This is our fluid. So this is our one particle. So here what is happening? This one is This one is gravitational force. This one is drag force, and this one is Bowen's force. So we are defining that gravitational force if G equals to particle into G, according to Archimedes' principle, this volume displaced by the particle will be volume displaced by the fluid. So net force acting on the particle, that will be F net equals to Fg minus Fd minus Fb. And we also know that F net equals to into acceleration equals to so when we are talking about at terminal settling velocity, where this acceleration terms becomes 0 and v becomes vt, it is represent like that. So from equation 1 we can get that So, finding on that we have derived the velocity expression. So, for a spherical particle, this volume equals to pi by 6 dp cube and projected area equals to pi by 4 dp square. So the equation becomes root over of 4 by 3 rho p minus rho f g into dp divided by c cd into rho f. This is for the spherical particle. Now we will move to what will be the case if it is at the laminar regime. For laminar case, this Reynolds number is less than 0.1. Here CD equals to 24 by RE, that is 24 d rho u by mu. So our equation was Vt equals to root over of 4 by 3 rho p minus rho f g dp by cd into rho f. So we are going to replace this cd that is 4 by 3 rho p minus rho f divided by 24 mu dp rho f into v rho f into g into dp. So it becomes Vt equals to Similarly, we can also derive for the turbulent regime, that is 0.44 at Reynolds number greater than 10 to the power 5. Here the velocity becomes, it was 4 by 3 dp rho p minus rho f by ct rho f. If we put the value of 0.44, you will ultimately get Vt equals to 1.74 root over of g dp rho p minus rho f divided by rho f. Similarly here, the drag force will be so this expression that we have derived, this will be used to do the numerical. So for this case, uh, we are going to solve our first question for this session. Let us solve this first question that we have derived for the terminal settling velocity. It is given that a spherical particle of diameter 45 mm is settling in a gas stream. The gas stream having density of 1.137 kg per meter cube, and the gas stream has the viscosity of 1.9 10 to the power minus 5 Pascal second. Now you have to calculate the drag force in unit of Newton units on the particle if it is following the free settling velocity of 25 meter per second. I hope this question is very straightforward. The data given here, the diameter of the particle is 45 millimeter. Which is 0.045 meter. The settling velocity is given 25 meter per second. The density of the fluid is given 1.137 kg per meter cube, and viscosity of the fluid is given 1.9 10 to the power minus 5. Now you know what is the drag force value, but before that you have to calculate the drag coefficient value. Now, what will be the drag coefficient value? You need to calculate what will be the Reynolds number. The Reynolds number is given by d rho u by mu. You calculate and let me know what is the value of the Reynolds number. Based upon the value of the Reynolds number, we will be able to understand that the flow here is a laminar flow or turbulent flow. Based upon that, we will decide the value for the drag coefficient. If you simply put the value you will have the Reynolds number 6.73 into 10 to the power 4, which is obviously denotes the turbulent flow. For turbulent flow that we have learned, the drag coefficient value becomes constant. It is 0.44. So the rest thing that we have to do, that what is the value of the drag force, that we can calculate using the equation. The equation is half of CD rho F ut square into AP. Now what is the AP here? AP can be also calculated for the sphere, that is pi by 4 dp square, which denotes AP equals to 0.00159 meter square. So if you put all the values here, you will get the straightforward answer. I hope you are getting the same value as 0.2486 Newton. If there is any question for the solved numerical, you may ask question that it is very straightforward to calculate and using the given equations for calculating the drag force. Then we will move to the next question, that a rigid spherical particle undergoes free settling in a liquid of density 750 kg per meter cube and the viscosity is 9.81 10 to the power minus 3 Pascal second. Density of the particle is given and particle diameter is given. You have to assume the Stokes law, it is given. So what will be the terminal settling velocity? So here the given data are rho F 750 kg per meter cube, mu F 10 to the power minus 3, particle diameter 2 into 10 to the power minus 4 meter, G 9.81 meter per second square, and rho P is 3000 kg per meter cube. Then you have to calculate the terminal settling velocity using the Stokes law. That is ut equals to g dp square rho p minus rho f divided by 18 mu. You just put all the values and calculate. Five into 10 to the power minus 3 meter per second. Now we are moving towards the next numerical, which is, it says that if the terminal settling velocity of a sphere particle A is 0.2 meter per second in a viscous liquid, find the terminal settling velocity for the spherical particle B of different density for the same size and same liquid. So if you remember, it follows the same. Uh, mm, you can just guess that, assuming Stokes law regime, we know that uh, terminal settling velocity is uh, proportional to the rho p minus rho f. So if you know that ub by ua is nothing but rho p a minus rho f, rho p b minus rho f, which is ub by zero point 0.2 equals to 10 minus 5, 10.5 minus 1.5, 19.5 minus 1.5. It shows uv equals to 0.1 meter per second. Now, when we are talking about particle motion under centrifugal force, so if an object is rotated in a container, it contains fluid and solid exerts equal and opposite force called centrifugal force, which is outward the wall of the container. And this force causing settling or sedimentation of the particles through a layer of liquid or filtration of a liquid through a bed of filter cake held inside a perforated rotating chamber. So here, similarly, if the net force acting on the particle will be external force, buoyancy force and drag force. This external force here will be replaced as here Fe, which is external force, is mass into acceleration of the particle, and acceleration will be r into omega square in centrifugal field. So the equation that we got, du by dt equals to ae rho ae by rho p minus cd u square ap into rho divided by 2m. You just r omega square, you just um, this value will be 0 at terminal velocity. From here you will get ut equals to omega root over of 2r rho p minus rho into m divided by ap rho p into cd into rho. This one is uh, terminal velocity under centrifugal force, where omega is angular velocity. So we have here our equation as ut equals to omega root over of r rho p minus rho into m divided by ap rho p cd into rho. For a spherical particle under resin, this m you can refer as pi by 6 dp cube into rho p, and a equals to pi by 4 dp square. So from there, having this modification, you will get root over of 4 by 3 r omega square rho p minus rho into dp divided by rho into cd. Now at Stokes regime, CD equals to 24 by RE or 24 by d rho u by mu. From there, you will, after substitution, you will get ut equals to r omega square dp square rho p minus rho divided by 18 mu. So from here you can see that ut at centrifugal and ut at gravitational under Stokes law condition, it is nothing but r omega square by g, this ratio. Similarly, when you have the Newton's law regime, for Newton's law regime Ct equals to 0.44, so the ut, the equation was 4 by 3 r omega square rho p minus rho into dp divided by rho into cd, that is 0.44, and you will get ut equals to 1.75 root over of r omega square rho p minus rho dp by omega rho. So this equation is for Newton's law regime, and when you have the uh, ratio at Newton's law regime, it will be nothing but r omega square by g. So now the thing that we learned about centrifugal force. Fc is always, that is r omega square. Now omega equals to v by r, which means Fc equals to v square by r, that is mv square omega square mv square by r. Now we will like to define the rotational speed. Rotational speed is capital N equals to 60 v by 2 pi r, which is the revolution per minute. From here, you can have omega equals to 2 pi n by 60, which is nothing by v by r. So, moving to this equation, we can also write Fc equals to mr omega square, which is mr 2 pi n by 60 the square. So this equation can also be, we can use this equation we can also use to calculate the centrifugal force in terms of the rotational speed. Similarly, uh, for gravitational force, we have mg. So here centrifugal force and gravitational force, we can have the relation. How the relation works, that Fc by Fg, it becomes 0.00118 n r into n square. This equation we were talking about. So next, we are moving to our last topic of this session. That one is hindered settling. So hindered settling is, as of now we were talking about free settling, and hindered settling is there are so many of particles or particle concentration is very large, so we have to consider the particle interaction and particle solid wall interaction as well. Hindered settling, it refers to the process where fall of the particle due to gravitational force in a stationary fluid is affected by the presence of the other particles in the wall of a container. In this process, the particles collide with each other and with the wall of the container also. Hindered settling is encountered when the concentration of the solids in the suspension is very large. For hindered settling, the settling velocity is considerably less than the free falling velocity. As the concentration of the particle in the suspension is increased, a point is reached where the particles are so close to each other that they no longer settle independently, and the velocity fields of the fluid displaced by adjacent particles, they overlap. There is also a net upward flow of the liquid which is displaced by the settling of the particles by the Archimedes law. This results in a reduced particle settling velocity in a hindered settling condition, that is also known as hindered settling. So hindered settling is also known as zone settling because it is easy to make distinct zones between the several settling zones separated by their concentration discontinuities. So as the suspension settles, the interface formed will move down at the same speed. So this is the well-known equation for calculating the hindered settling velocity. So the US is the suspension settling velocity, which is related to the terminal settling velocity, also related with the porosity of the suspension, or also known as volume fraction of the suspension or liquid, where n is the Richardson-Jacky index. This index value n is of 4.6 for Stokes regime, where particles Reynolds number is less than zero point 0.1, and this n value is 2.5 for Newton's regime where particles Reynolds number is greater than 10 to the power 3. So we will now go for the numerical for the hindered settling velocity. So it says that 30% by volume suspension of the spherical sand particles in a viscous oil has hindered velocity of 4.44 meter per second. If the Jackie-Richardson hindered settling index is 4.5, then you have to calculate the terminal velocity for the sand particle. You have to calculate the ut, where the uh or us is already given 4.44. N value is given 4.5 and volume suspension of the particle is 30%. That means it will be void fraction will be zero point 0.7. Then you have the equation, right? us equals to ut. Then you calculate the value of ut. 4.44, zero point 0.7 to the power 4.5, which is coming around 22.10 meter per second. This is very straightforward, simple equations. Similarly, we will solve the last question for today's session. Here it is showing that single silica particle which is insoluble in the solution having terminal settling velocity is 0.018. You have to calculate the same hindered settling velocity for the same particle where the volume fraction is zero point 0.4, which is 1 minus zero point 0.4, which is 0.6. A constant value is given 4.6. Then you have to calculate the hindered settling velocity, which is us equals to ut 0.018 into 0.6 to the power 4.6, which is coming around 1.716 millimeter per second. So we have discussed a lot about numerical question for today's session. Hope it will be helpful for you to solve the um, assignments for this topic. And we discussed a lot about things related to free settling, hindered settling. If there is any question regarding today's session, you can drop me email about your queries, or you can join next session. We can also discuss in the next session. So I will request you guys to join for the live session to clear your doubts. And in the next class, we'll be discussing fluidized bed and packed bed fluidization conditions. So, I would like this session to end here. Thank you for joining. We will meet in the next class. Thank you.